So, good afternoon, at least from my perspective, also to all of you, no matter what time it is at your place. And I try to share my presentation with you and hope it will work out. Look good?
Yeah,
so
perfect.
Today's topic will be function and design of coaxial connectors, with focusing on SMA connectors. For a certain reason, it's the widest portfolio where we have the most possibilities in our portfolio, and it's the widest frequency range. So it's the biggest challenge to really make them work. But the basic principles we will look at are, of course, valid for all our coaxial systems that we are carrying in the portfolio. For the beginning, we will have a look at coaxial systems themselves. What is it? What parts are contained? How they're set up? What is quality points for coaxial connectors? Then we will have a little bit of a review on basic RF engineering to catch up the most important points. And finally, we will have overview on different PCB structures in use and setups. And we are done with this. When we are done with this theoretical part, we will have a closer look on the combination between connector and PCB, because this is the critical point where you change geometry and material and where you definitely will get losses by reflection. And we will try out to keep the losses as low as possible. So let's start into coaxial systems. And for the beginning, of course, I will also have to tell you a little bit of our portfolio. So the focus will be, of course, as said, our SMA connectors, but we do not only carry the SMA connectors, but we start with UMRF, what you know on the market as UFL, as a very tiny connector, up to the N-type connectors, quite bulky connectors known from GPS antennas, including all the cable assemblies necessary, also customized, and all the needed adapters to interconnect different systems. I just want to point out one special, because this is not very well known by everybody, and this is in our SMP portfolio. So I don't know if you are aware that in the SMP portfolio, I need to go back to my normal pointer. Now we are here. I recorded a little video to explain to you. So you have here the possibility to do board-to-board RF connections with SMP. You can see there is this little bit of distance holders in two different lengths. And you have the SMP connectors, one in limited detent, one in smooth bore. Limited detent means it will snap in with a certain force. Smooth bore means it will just slide in. So this gives you the opportunity to create a real board-to-board connection where the distance holders for the signal that carry the signals will be stuck on one side, so you can still unmount the board-to-board connection without losing any of the parts, as you will see in a moment. So just an option that is not known by everybody, so that's why I'm highlighting it. Enough for the products. Let's go for coaxial system types and what is inside. So we have here typically, of course, plug and check as complementary parts of the coupling system. We have PCB connectors in different soldering styles, from THT to SMT to THR. We have different cable connector styles, adapters, and we have panel connectors not only for soldering to a wire, but also for the use in microwave boxes according how the back shape design is realized. So in this case, of course, it can be very helpful and make your life easier. In addition, we have different cable types depending on frequency range you need, and the interesting thing is you can have them as well customized and in matched pairs and matched matched quads, so that you have really the same parameters or specification on all of your cables. And finally, there is some tools, especially important in the SMA portfolio, like the torque wrench. It can be ours, can be made of a PCB piece that breaks when the torque is too high. Of course, I prefer ours. But this is really important when you're working with SMA, because the thread is, or the whole body is made out of brass, so it's not too strong. And if you tighten it too much, you will, of course, deform the thread. On the other hand, if you just screw it by your fingers, it will probably not be tight enough to really close, and you will get some leakage by radiation. This is why the torque wrench is important. On the one side, we have the typical end lunge connector. This is very popular, but it's made for a fixed PCB thickness like 1.1 or 1.6 millimeters. So you have no other choice to use it for other PCB thickness. It's available with two different signal pins, so flat tap or a round post. As another option for it, we have in the nearly same geometry the full SMT version, which is a PCB mid-mount, so it's sitting in a cutout in the PCB, and the flat tap is going on top of the PCB on the backside, so it's not limited by the PCB thickness because it's sitting inside and on top. So this is a good alternative if you have PCB sizes that does not fit to the end lunge connectors. As a vertical version, of course, there is also a full SMT that we will have a look on, but unfortunately, I mean, it's good for the pick and place process, but from mechanical force and retention on the PCB, it's of course not as strong as a through-hole version. So this is why we have also a look on the THR version, where only the ground pins are THR and the signal pin is SMT. So let's go for the next one. So the mechanics of coaxial systems. If we go to the mechanics, of course, we also have, like for every connector, an interface part to interconnect with the opposite. And we have a body that defines the mechanical fixation on PCB, housing, or cable side. If we have a closer look on female and male parts, we see if we split them up in their parts it consists of. For both, we have a housing which is made of massive brass and is plated with gold. Then we have the central contacts, we have the insulator, and of course, on the male side, we have the hex nut, the coupling nut, plus gasket and C-ring to fix it and to allow it to move. So what is the difference now, or what is important? The contacts is the one point. The male contact is normal pressed contact out of copper alloy, gold plated, because it does not have to move really. On the female side, and this is a point you can watch out for quality, you usually do not use a standard copper alloy stamped contact, but you use copper beryllium contacts or related materials that are more flexible and will not wear out so early, so they can still the same tension, keep the same tension over all the 500 life cycles, or if they are connected for a long time, to provide the same performance in electrical resistance and all the technical data, so that your signal transmission is stable. Another point of quality that you can see is if the center contact is made out of one piece and slided into the housing, or if it's made of two pieces and soldered on the corner. So you have additional material here, you have different material here if it's soldered, which will of course cause you some reflection in your transmission. So this is points where you can easily see from the mechanical aspect if this connector is really made for the high frequencies, or if there is some, let's say, limitation already below. On the other side, we need to ensure not only that this center contact is very stable and right in the middle in a very good symmetrical way in the housing, but we also need to make sure that the insulator cannot move, neither in rotation way nor in axial way. And this is realized with different structures we are using, and this is also something you can experience by yourself if you check out really easy, cheap SMA connectors to let's say known brands. That sometimes if you unplug, you feel a little bit of a movement in there, where the electric material starts to slip, to slide. And this is of course something we want to avoid, because if this slides, we have an air gap somewhere. So we again have the problem of changing materials and getting reflection. So how to do that? We try to use structures like here, like shoulders or like barbs that are pretty big, I would say. So in this case, it's for the lower frequencies, because the structures are quite big. And if we go to the high frequencies, we use smaller structures like the straight nulls and the crossed nulls that are really fine cutted or milled structures in the surface of the contact that make sure that the insulator cannot rotate. On the other side, we need to make sure that it stays in place also on the axial way, and this is done by using swagging options, bending options here in the back to ensure that it cannot slip out. The easiest way is this kind of dimples, of course. This is just bending in the metal, but of course it's not the finest structure you can get. If you want to really get to small, fine structures, you can use, for example, the internal barbs that are directly milled into the housing, but this is of course a lot of effort in the milling process, and so costful and only used more for the high performance connectors. On the other side, we have already heard, when we go to the contact side, that we have blunt post and flat tap contacts on the SMA connectors. Not only on the end launch connectors, but also on other types of SMA connectors. And we have a solder cup, so for soldering the wire, but I don't think we need to talk about it, as this is well known from different parts like D-sub connectors and stuff like that. So let's go to the blunt post and flat tap. What's the difference and what's the benefit of which? The blunt post is a quite big and strong signal contact at the back of the connector, and it's of course mechanical stable. It's good usable in lower frequency areas or in PCB stacks, for example, 2-layer stacks that are having a quite wide transmission line, so where you have space, and it's quite good to solder. The flat tap on the other side is good for PCB stacks like a 4-layer coplanar waveguide, where you have quite small transition lines. So the flat tap will not bring a lot of additional capacitive problems, and it's easy to design there. But the mechanical capability is of course limited. So if you slide this kind of connector on the PCB, you might take care not to hit the corner with the flat tap contact because it's bent easily. And also, if you solder it, take care not to use a lot of solder paste because this will bring you additional parasitics on the capacitive side, which, let's say, negotiate or which limit then the positive impact of having this really small tap on your transmission line. And what can I do if I have the problem that I need a different PCB thickness than the 1.1 and 1.6 that is possible with the end launch connectors? You could go either to the SMT solution I showed you in the very beginning, or you could go, if you need more mechanical stability, to this kind of connector you see on the right side, because here you have the interface like on the end launch connector with a flat tap coming out here, but you have these claws, I would say ground claws, ground posts in THR that are strong on the PCB side from the mechanical aspect. Of course, we carry the SMA in standard and reverse polarity, which is easily explained. The standard type you have for the female body, the outer thread, and inside, of course, the female center contact. And if it's reverse polarity, you have the same outside housing from the female body with the outer thread, but you have the male pin inside. Of course, for the male connector, it's the same basically. So the male housing contains the hex nut and the male pin for the standard version, and for the reverse polarity, you have the male housing and the female contact inside. With these options, you can choose your connectors so that you can code with your incoming, outgoing line, your antenna, and so on. So you cannot connect your cables or your antenna in a wrong way to the wrong connector. Typical operating temperature for our connector range here is -65 to +165, which is quite wide, of course, due to the PTFE material. We have 500 mating cycles, and we can go up to 18 gigahertz with our SMA range. Just a little summary for the handout so that you have it in mind when you download the handout. And now we will jump to the basic RF engineering. We will talk a little bit about wave characteristic, about reflection and attenuation, the S parameter and VSWR measurement, and about discontinuity and TDR measurement. Let's start with the wave characteristic. Of course, we all know what is the frequency. So it's the number of cycles per second, and it's F in Hertz. Very basic. And if you go a step further, the wavelength is, of course, lambda is C divided by F. So means the higher my frequency gets, the shorter the wavelength will be. So at 1 gigahertz in air, of course, we have 30 centimeter, 2 gigahertz, 15 centimeter, 4 gigahertz, 7.5 centimeter. If you already heard, I said in air. So this means there is, of course, an impact also of the material where we want to transmit our wave. And this is, of course, the influence of the electric material. So air has an epsilon R, so the relative permittivity of 1. If I now go to a different material, we will see the impact of the epsilon R, because if I say lambda is velocity of propagation divided by frequency, and I look at the velocity of propagation is C divided by square root of epsilon R multiplied by mu R, I have here my material constant inside. And this means if I send my wave throughout the different material, I will change my wavelength. And This is really crazy in a first thought, but this is explaining why we really have issues when we change the material. So if we go from a PTFE material in the cable to the PCB with FR4 material that has a different epsilon R, because then we will stretch or bend our wavelengths. And this is, of course, what is causing trouble and reflection and loss of energy. So the example air, like we said, 1 gigahertz has 30 centimeters. But if I do the same 1 gigahertz through a PE material with an epsilon R of 1.5, I have only a wavelength of 25 centimeters. And if I go to PTFE with epsilon R of 2, I have only 21 centimeters. So it's quite a big difference between air and PTFE. And this explains also why it's so important, for example, to really fix your PTFE insulator interconnector so that it cannot move and make any air gaps, because this will cause you a lot of trouble. So this is really a point to look at in the quality of the connector. Then we need to know about the wave impedance. So this is the initial impedance of, or the intrinsic impedance of the traveling wave that is only affected by the environmental parameters μr and epsilon r. So relative permeability and relative permittivity, so for magnetic and electric field. And typically the impedance of the traveling wave, or the wave impedance, is 50 ohm. What we now need to do when we want to transmit this wave, we have to match our line impedance to the impedance of the traveling wave. So we have this 50 ohm wave from the source going to the 50 ohm load, and we have to take care to create our transmission line in a way that we perfectly, or as perfect as possible, match to our wave impedance by choosing the right material and choosing the right geometry. Geometry, why does it have influence? We can see very well here in this example of the coaxial connector or a coaxial cable. It's the same here basically. So we can see that the characteristic impedance is 138 ohm divided by square root of epsilon r. So we have here the material parameter inside, multiplied by the logarithm of capital D divided by small d, which is the capital D is the inner diameter of the outer housing, so the outer limit of the dielectric material, and the small d is the outer diameter of the inner pin. So this defines the thickness of the dielectric material. So this is why the geometry also has to be taken into consideration with our transmission line. Now, what will happen when we transmit a signal? In an ideal world, we would have a perfect match between source, transmission line, and load. Everything perfectly, impedance of 50 ohm. In reality, it will never happen. So we have a source, we will have mismatches on our transmission line, and also in between the transmission line and the load at the end. Each mismatch will create us losses by reflection, and so we have to find out what kind of losses we have and how we can deal with it, where they are located, and what can we do better at this spot. The losses we will have are, on the one side, absorption in the dielectric, because there the electric and magnetic field are traveling and are pulsing, and there will be, of course, some kind of resistance where we'll lose energy. We will have heat loss, so the Joule effect in the conductor, like always when we transmit any signal in any copper wire. And we have radiation loss, so leakage to the environment because of non-perfect shielding, non-well closed SMA connectors, things like that. Slot antennas that we might create somewhere in our design. And we will have reflection losses that are caused by the variations of our line impedance. So by changes of material, changes of geometry, things like this. Now, how do we find out where we have losses and how much it is? We can do different kind of measurements. At first, to measure our throughput, we can do a measurement of a S21. So we send our signal through our transmission lane and see what will be, let's say, left at the end. So we will see how much energy, how much signal we lost overall. But this does not tell us how much signal we lost in reflection, where we have the problems with a mismatch. It just shows us the overall loss. To look at the losses through reflection, we do a measurement on the S11. So we send the signal to our device under test and we look what's coming back, what is reflected. And of course, this is then what is caused by our mismatches of the impedance. There is also another option how to do that. If you don't want to go for the S parameter measurement, you can also go for a VSWR measurement where you compare the forwarded voltage to the reflected voltage. And of course, we are here in the voltage domain, so we have the logarithms on a base of 20 here, and that's also a way on finding out how many reflections you will have. To compare these two options, let's have a look at the table. So if we are talking about the VSWR, the best value you can have is 1. So if you have 1, you have a perfect match and you have no loss. And the higher the volume gets, the value gets, the worse your matching will get. So up to a point of 1.4, we talk roughly about a matched system. And if it's getting higher, we are poorly matched or not matched at all. For the return loss, it's exactly the opposite. The best value for the return loss you can have is infinite. And then, of course, the lower the value gets, then the poorer your matching will be. Up to a value of around 15.6 dB, we talk about a matched system. And if the the value gets lower, then we get to the poorly and not matched areas. Just as an example, if we have a loss of, or a return loss of 15 dB, we talk about having 97% of signal and 3% of reflection. If we have 10 dB, we are 90% insertion and 10% reflection. If you are down to 6 dB, we have only 75% of insertion and 25% of reflection, which is really huge. So it's really considered to be above the 15 dB, definitely. What to do now if we have recognized that we have losses by reflection? Where do they come from and how to identify? So they come, of course, like said, by the impedance variation on the RF path. That can be caused by geometry, so jumps from high impedance to low impedance, or the other way around from so it can be geometry, it can be change in material that cause these reflections, and of course cause field conversions, and so this will lead to discontinuities that cause the reflections. We can identify where this reflection happens on our board by doing time domain reflectometry measurement. So TDR measurement. And how does it work? We send a defined pulse from the source on our device under test, and we measure on the reflection as well the amplitude, but also the time where the reflections, how long it takes. And we get a diagram, impedance over time, which is looking like that. And this is, for example, a typical example for a connector on a PCB board. So you come in with your signal, you have to change in the geometry and in the material. And then when it goes out of the connector, the signal swings in around the 50 ohm and becomes stable. Of course, we can not only talk about the time here, but it can be recalculated also to the lengths so that you can find out where the hotspot or the problem on the PCB side is. So the wave, let's sum up. The wave impedance depends on the E and H field, so depending on mu r, epsilon r, and is typically 50 ohm. We can measure with S parameter the reflection and the throughput, so we can identify our overall losses and our losses caused by reflection. And we can also identify where our reflection happens on our PCB design by measuring with TDR and identify where the critical places are to rework. Then let's have a closer look on the PCB structures. What are typical layer setups in use? So of course not all, but typical ones. What types of planar transmission lines are in use? And what can I do to make it easier or to optimize my layout? First is typical use is a two-layer system with 1.6 PCB in FR4. They typically have no separate ground plane elsewhere. And on the other side, what we find is typical four-layer setups with 55 height and FR4 material that allow to have a separate ground plane for the RF layer. And of course, that makes my life a little bit easier. What needs to be taken in consideration is, on the one side, that if you have a layer stack of a PCB with all the different layers laminated to each other, you have a pre-preg. And this means that your copper layer do not all go 100% to the edge of the PCB, but there is 1 or 2/10 of FR4 material in between, which needs to be known, because otherwise you will create a great slot antenna. Of course, there's different options like metallized edges of the PCB that cost money. For many cases, you don't need that, but you can also close your gap antenna in a different way, which we'll see in the simulations afterwards. The second point to take care of is PCBs are made of course, woven glass fabric and resin. And this combination of glass and resin is not the same for each manufacturer. The same like the fabrication environment is not the same for each manufacturer. So this means if you have designed a working RF PCB with FR4 and it's working with one PCB manufacturer, you cannot just order the same at another one, but you have to really make sure that the ingredients and the relation between the ingredients are the same. Otherwise, you can really have an issue not to reach the same performance in RF transmission on this batch of PCBs then. So this is has to be taken in consideration and to be checked precisely before signing the backup delivery. So, planar transmission lines, what is typical? On the one side, strip lines, which consist of a ground plane on top and a ground plane on bottom, and in between the transmission line is embedded in the PCB, which is very good for the radiation or to avoid radiation, of course, but it's a little bit complicated if you want to add additional components like capacitors and so on your PCB track, because for each component you have to make a wire to go to one of the top layers or bottom layers, implement your part, go back with a via to the transmission line, and each of the vias, of course, will cause some impact, will cause some reflection and some mismatch. So you want to avoid that, of course. Then we have the microstrip, which is very popular, especially for patch antennas, where we have one RF layer on top side, and we have a separate ground plane on the opposite side of the PCB. So it's a two-layer system. We have the grounded coplanar waveguide, which is on the RF side. You have the transmission line, and you have the guiding ground planes beside left and right, and below that you have an additional ground plane. And finally, we have the slot line, which is an unsymmetrical system where you have on one track the RF transmission line, and on the other the ground plane. This is existing in different versions, like besides here, but it can also be one on top, one on bottom, and shifted besides each other a little bit diagonal here. So there is a couple of options how to do a slot line. We will focus for now on the microstrip and grounded coplanar waveguide because this is the most popular ones. So typically the microstrip has a wider line width for the transmission line. It's used typically as antenna fed line and has no ground on the RF layer. The line width depends on the height of the substrate, so the thickness of the FR4 here, and of course on the epsilon R of the PCB material. For the grounded coplanar waveguide, we have a smaller line width. We have the possibility to do ground connection, two components, because we can place them in between the transmission line and ground here directly on the surface without needing additional vias. We can also compensate the parasitics on the capacitive side that is coming in with the connection of the additional parts easily here on the ground plane. And so we have a lot of options for planar matching designs. And the line width here depends not only on the height of the substrate and the epsilon R, but also on the width of the gaps here between the signal line and the ground lines. If we compare it in the simulation, we can see that the spread of the field is much wider on the microstrip and on the grounded coplanar waveguide, because we have here the ground plane directly below, ground plane left and right. We have a more focused field, less field spread and less radiation. And the typical use, like said, microstrip antenna, or for components, the coplanar waveguide. How does the different parameter influence the impedance? So if I increase my width of the RF track, then my impedance will decrease. If I choose a material with a higher epsilon R, my impedance will decrease. If I increase my gap in between the transmission line and the ground planes on top in the grounded coplanar waveguide, my impedance will increase. And if I increase my substrate height, also my impedance will increase. Always given, of course, that the other parameter stays stable, because they influence each other. So if you change all, everything will change, of course. Yeah. Good. What can I now do to make it easier or make my transmission more stable? I can, on the one side, decide not to use solder resist on my transmission line and the ground planes beside in the coplanar waveguide, for example. Why? Because it adds additional dielectric. So the solder resist has a different epsilon R than the FR4 material has. So we will have field conversions in this point, and we have mismatches. And the other thing is that the solder resist is never really even. On one place, it's a little bit thicker, on the other thinner. And if you look on this on a microscope, it's like really like a wave area. And this is, of course, not a structure that is ideal for a perfect transmission. So if it's possible, you can leave it away. I know it's not possible for every application. It depends on where it's in use, how the environmental parameters are, and so on, but it can be helpful to know. The other thing is you can use a wire fence. If you're in a coplanar waveguide, what does it do? So if you look, we have our coplanar waveguide with the RF transmission line, the ground planes left and right and below, which was already pretty good before. And if we now use the wire fence, we will concentrate our field spread even more. We concentrate our field more on the transmission line area, so we have less losses and reduced coupling by stabilizing our ground planes, because this is like a ground cage surrounding our signal, which is very helpful. So a thumb rule would be the distance between the different vias in the via fence would be something like 4 times the gap width between transmission line and the ground planes here, or about 1/10 to 1/20 of the wavelengths you want to transfer. So, and of course, it's very helpful to have a separate ground plane that is dedicated for your RF layer. So you can use this kind of tools like a via fence to reduce loss. Then it's of course helpful not to set vias inside the trace in the transmission line, because of course this will create mismatch as it's not even anymore. So you have geometrical changes, which is not good. And so this is the basic rules where you should focus on to allow a good signal transmission. And then finally, if it comes to the point of optimizing connection points, no matter if it's the connector itself or if it's a capacitor you want to add on top of the transmission line, you can use taper structures. So if you're in a microstrip environment, you can use line taper and work on the transmission line itself. And if you are on the coplanar waveguide, you can work with the ground taper. What do the taper structure do? Well, if you look on the top left for the line taper, basically we have here in the open area our 50 ohm line crossing the PCB, optimized for the height, for the epsilon R and so on. But in the connector, we see we have ground here, we have ground here, and here the signal. So this is behaving like a coplanar waveguide more or less here in the entrance area of the transmission. So we need to take care what gap width we need here to be in this area on 50 ohm. So we will have a different line width in this connecting area than we have on the rest of the PCB board. And to match this and to allow a smooth transmission from the small PCB track to the wide one, we are using taper structures like this, which are in relation to our frequency, always in a lambda quarter relation. So how they build the curve, because it's a little bit like you try to drive with your car on the sidewalk. If you choosing a point where you have a high sidewalk and like these right angled big bricks, and well, you can go up there, of course, but you will feel a lot of force coming back to you that will be shaking you. But if you choose to put some small piece of a triangle of wood or whatever, you have a ramp and you have a much more smooth way up there, where you have a lot less force coming back to you when you drive up. So, and this is more or less the same what the line taper does for our electric field. For the signal transmission, it allows a smooth transition from one side of the PCB track to the other. And that's the same more or less for the ground taper. The ground taper finally compensates the additional parasitics, the capacitive parasitics you bring on the PCB track, because you can imagine if you set on this small PCB track a pin like that, it brings additional material, so you will have a capacitive parasitics that cause an impedance mismatch, and with that you want to compensate by putting away here some of the material of the ground plane. And in case you have so much parasitics on the capacitive side that you cannot realize by changing your ground plane on the top level, on the top layer, here with the ground taper, you have in addition the possibility to go in the ground plane below and make a so-called DGS structure. So a defective ground structure means you cut out also a piece of the ground plane there below the connection area to compensate the parasitics. And we will later see in the simulations that this is really working. So again, summary for you for your papers when you download it. And now let's go to the combinations between connector and PCB. What are suitable combinations? What RF effects do we see? And well, how does it look in practice when we simulate it? What we will do, we will use blunt post and flat taps in different connector combinations. Blunt post suggested at lower frequency, flat tap for higher frequency. Blunt post suggested to be used on wider tracks, so more in the two-layer system with microstrip typically. Flat tap used on smaller tracks, so would be typically a four-layer system with a coplanar waveguide. And now we try to place the connector on the PCB board and see what will happen. So the big issue we have that we will create a lot of discontinuity at the connection point, because we have a huge change in the line impedance, and this will cause a lot of field conversion. Why? We try to match a round transmission system to a squared one. Yeah, here you can see it very well. So that's how the field spread is in the coaxial connector. And that's the field spread on the PCB side with the coplanar waveguide. So yeah, trying to match circular to rectangular and trying to match different materials. Here we have the PTFE and here we have the FR4. So this is really a challenge. And if we do not react on it and not optimize our layout for this PCB, we will have huge mismatch and reflection. And so that's why we need planar matching circuits. If we look exactly at the point where the connector ends and the PCB begins, we can see a really huge field spread there. And well, you can imagine that not all of this energy will exactly go on this small transmission line here if we do not act and optimize our system. So what are the steps to do? Let's start with the first one. We take this one we saw in the beginning with the hooks and the flat tap on a 2-layer system with a microstrip. This we will do in 3 steps. We take first the PCB layout, the datasheet layout, and then we try to optimize it step by step. So for the other ones that we will look after, so we will look at a end launch type with flat tap and compare it to a blunt post in the same system to see the difference in the effort. And we will look on how to use one of these verticals with the THR ground posts. We just show the final solution and explain it. Our given limits are we want to stay in the impedance between 54 and 46 ohm. So of course, ideal is 50 ohm that we can never reach. So we will always have a little bit of a mismatch. And on the matching side, we want to stay in the frequency range up to 6 gigahertz, below -20 dB. And then from 8 gigahertz on, we want to stay below -15 dB. So start with the first one. Our hook variation with 2.8 millimeter PCB, 2 layers FR4 with microstrip and an application for a patch antenna. Let's start with the datasheet design. Then we see the worst case and then how it should be. On the datasheet design, we just have the vias here given for the mechanical fixation of the ground pins. That's it, more or less. So we just create a 50 ohm microstrip line for that PCB layer stack, and that's it, more or less. Bring it into the connector and done. What will happen now? If you look at the simulation, we can easily see that in the connection area, of course, we have some hotspots where our signal transmission is as to expect, not perfect, and we lose energy. Where do the most losses come from? Let's have a closer look. Okay, we have some EMI problems because we have radiation here created by a slot antenna. Here, this is our prepregs because this connector is just set on the PCB, but because of this 1 or 2 tenths of FR4 on the prepreg, there is like an air gap and we have a slot antenna. So that's an issue we have to solve. And the other thing is that we do not really have a complete ground connection. We just have these 2 little pins that go on the PCB here as ground, but not in the first moment where it comes to the PCB. So the first thought we want to do is optimize ground, because I think we can do better than we can see here. So we have here in the first step an impedance mismatch, which is still on the okay side, but it takes very long until it stabilizes. And if we look on the frequency side, on the S parameter, we see that we only are below our limits, let's say up to 6 gigahertz, but the connector should be able to do 18 gigahertz. So there is something to do still. The first thing, optimize the ground connection. What we are doing is, instead of this one via, we set a second one, like a little via fence here, because we said it's behaving like a coplanar waveguide here in the interface part, and make a good ground plane here that we really have the ground from the beginning rim of the PCB. On the bottom side, we create a pad on the ground to the ground layer and close it with solder, so to have the connection to the housing and to close this slot antenna we recognized in the first simulation. And now we have a good ground connection, a really good ground connection, and we see what it will do. So, and we can still see that, of course, on different positions, but we still have some red hotspots in here. Like before, So let's see what impact our improvement had on our measurement. And we can see, yeah, it worked to close our slot antenna. That's a good sign. So no radiation anymore. The energy should be hopefully on our PCB track and not somewhere else on the PCB. TDR measurement. Whoa, great. A huge capacitive mismatch right in the entrance. Boom. But then now the signal stabilizes quite fast. And if you look on the S parameter measurement, what shall I say? Yeah, we do not reach even 2 gigahertz, even worse than before just with the datasheet measurement. Why is this the case? Because we forgot one important point. I jump back. We added here these ground planes to optimize the ground connection for the whole connector, right, from the front of the PCB, which is a good thought. But now it really behaves like a coplanar waveguide, and this means that the gap width here, left and right, has a lot of influence or defines how wide our PCB strip here in this area must be to fit to the 50 ohm of impedance. And this is what we did not correct. We just left it as it was and just changed or optimized the ground here. And this is the reason why we have now this huge mismatch in directly here in the interface part. And now, in the second step, we optimize our transmission line so that we also fit in this connection area to the 50 ohm and use a line taper structure to come from the small width of the transmission line to the wide size of the transmission line. The rest will stay the same. We still have our ground pad on the bottom side to close the air gap. And now we will look how it will behave. And we already can see here that the hotspots got a lot less, so it looks much better than before. And still, our slot antenna is closed, so it's not causing us EMI problems and radiation problems. And we can also see, even if there is still a little bit of an overlap in the matching in the connection area, it's not critical. So it's a little bit above what we defined, but it's not in a critical area, and it stabilizes quite nice. And if you look at the S parameter, we can see that we are now really going up. Of course, here's probably half a dB of mismatch, so we have a little bit of deviation. It's not perfect yet. There's still something to do, but you can see that with this tool, you can really optimize the performance of your connector, of your connection. So very helpful. In the next step, we will compare the end launch connector for 1.6 millimeter PCB with flat tap to the one with blunt post. We will use both on the 4-layer FR4 PCB. Even if this one is suggested, the blunt post is suggested normally for the 2-layer, but as we want to see the difference in design effect, we use the same basic system to bring both connectors on because they're identical besides the pin. And then we can easily see what's the difference in performance and the difference in effort doing the design for it. Let's start on the top layer of the PCB. So we have a coplanar waveguide with VFNs. What we did, in addition to the datasheet layout, which is just the mechanical characterization, but not the full PCB layout, as we don't know what PCB layer stack you will have at the end and what material, so it's impossible to give you that information on the datasheet. We optimized here the ground connection. So you can see we really start here to completely make a good ground connection on the top side. We compensated the capacitive parasitics brought in by the flat tap by doing here a ground taper structure. And on the blunt post side, we did the same with the ground connection, of course. We did also here a ground taper structure as big as possible to compensate the capacitive parasitics. And what we also had to do is to make a solder pad for the blunt post, because it's so huge that it's hard to solder it on this little PCB track on the 4-layer system. So it needs some space to sit on where it can be soldered. What else did we do? For the flat tap, of course, we added as well on the bottom side, again, the ground pad to connect to solder to the housing so that the slot antenna is closed, and that's it. So let's have a look on the performance of the flat tap type that we optimized. And we can see, oh, this is looking pretty nice here. There is not really hot spots here. We are not losing too much energy. And if we look on the measurement, we can see that we are pretty nice in the area we defined. There is not a huge mismatch in the connection area. So this looks pretty good. And on the S parameter, how is my matching looking? Yeah, we are everywhere up to 18 gigahertz below the limits we defined for us. So looks good. Pretty well done, nice job. That's the performance we want to see. Now let's have a look on the blunt post. I already explained you what we did on the top side. Basically on the ground optimization, it's everything exactly the same on top and bottom like for the flat tap. Just the added solder pad, as this pin is so big, and a bigger, of course, resulting a bigger ground taper to compensate the parasitics. And what we needed to do, because there is simply not enough space in here on the inside the connector area to compensate all the parasitics brought in by this huge pin, we needed to make a defective ground structure in the layer below to optimize that. So, and with that, let's see what kind of performance we got. And it's looking pretty nice, because still we can see that here there is no real hotspots. Here is a little bit more than on the other side, but still it's pretty looking okay. And if you look on the measurement on the TDR, we can see, yes, the deviation is bigger than we had with the flat tap, but it's still in the area we defined as a good one. And on the other side, for the S parameter, we can also see, oh yeah, we are still below our given limits over the whole frequency range up to 18 gigahertz. We are a little bit not as good as the flat tap in this area here. But finally, you can see that it's also possible to use the blunt post for going up to 18 gigahertz, but the effort in doing the design is simply higher. You need to create the solder pad, you need to have the DGS structure, and you need to find a way to do it in the right way and the right amount that you remove. So it's a little bit more tricky, whereas with the flat tap, you simply can compensate everything on the top layer, which makes your life much more easy. And then finally, what we also did is to put this vertical version with the THR ground posts and the SMT signal pin on a coplanar waveguide 4-layer system with 1.6 millimeter. And what we did here is we did a simulation once, including the ground taper structure and the DGS structure, and one simulation to compare where we only did the ground taper structure, but we did not do a DGS structure to show how big the impact of the DGS structure is, because that's always a little bit, let's say, hard to grab. Be talking about, yeah, I make a ground structure here, make a DGS structure here, but how much impact does the ground structure have, and how much ground taper have, and how much does the DGS structure have? Hard to imagine. So that's why we compare it to each other. So at first we put this part on top of the PCB, of course, and we have the via fence running throughout it. As it's a circular system, the via fence is of course going around, and we are doing a ground taper, a circular ground taper in this case here, to compensate the parasitics. And as this pin is quite massive that is sitting on top here, it's also necessary to compensate fully the capacitive parasitics that you do an additional DGS structure. In that way, especially as we are limited with the space below here. I mean, we have the ground posts here on the corners, we have the via fence running around, so we are limited in the space also in the material we can remove on the top layer. And so we also have to make the DGS structure on the ground plane below. And now we will see how big the difference is. Let's have a look at the TDR measurement. The blue line is only ground taper, no DGS structure. The red line is both. And you can see without the DGS structure, we have a huge mismatch in our connection area. And with the DGS structure, we clearly stay very much in the area we defined as a good one. So here the DGS structure is a real game changer. It's really very helpful to use it. And we will see the same, of course, in the S parameter measurement, where we can see without the DGS structure, well, we come up to an area about a little bit more than 2 gigahertz, and we are out of our specification that we set ourselves. And with the DGS structure, we go up until something like 15 gigahertz, which is for a 90-degree angle sit on top pretty much. That's pretty nice, and I'm pretty sure we can also still give it some additional optimization to probably go up to 16. And so to stay within our limits, so you can really see the use of the DGS structure is very helpful. So means you see that it's easier to use the blunt post for the lower frequency range and microstrip line, for example, where you have big transmission lines, and the flat tap where you have coplanar waveguide or structures where you have small transmission lines. And do not only take care on the ground connection. Of course, you should. A stable ground connection is very, very important, but take a look on the whole connection area to optimize and not to oversee something like this effect that in this connection area it's behaving like a coplanar waveguide, and then it's becoming a microstrip line here, so that you have to take care also on the gap width here. Otherwise, of course, mechanical conditions, electrical values are important to choose the correct SMA type. If we go away from SMA, of course, the assembly type, how fast it should be, what frequency range you need, and so on, is relevant for choosing the right connector. The structures and PCB setup you want to use is, of course, a big point for choosing the right connector, and using the right tools in the right amount, like all the taper structures, DGS structure, via fence. And if you handle that in a good way, you saw that you can really optimize your transmission, and you can really keep your losses in an area where you say, okay, I can deal with that and it's working. And that's it, more or less, for today. Sorry for the dropouts in the beginning. Somewhere my computer was stuck, but finally we made it. And yeah, Marcus, I'm done. It's time for questions.
Yeah, so thank you very much from my side also for your interesting presentation. And yeah, as Thomas already said, now we would like to turn our attention to your questions. So we wait a little until some questions come in, but I can also see the first question already. Thomas, what are the most important selection criteria for high frequency connectors?
Well, basically, that's going back to what I said at the very end of the presentation. Of course, most important is frequency range you want to cover, and of course, impedance. The connector must fit to the impedance of the system you want to work in. And then, of course, we are coming to the point where we are talking about layer stacks, PCB thickness, and so on, which will give you some limitation as end launch connectors will not work for everything. So that's why we have a couple of options to use for different PCB sizes. And finally, it's about how you want to assemble. Are you able to screw, of course, mechanically and electrically the hex nuts and the locking of the SMA is very good and stable, but sometimes you want also to be fast, and then it's probably better to go for SMP or MMCX, or you need to be very, very small, like for Bluetooth modules and stuff like that. So you better go for UMRF, which is pretty standard there. So that's mainly the characteristics.
Perfect. So thank you very much, Thomas. Yeah, then let's go on with the next question. Is there any application node specific for UMRF?
No, it's not specific for UMRF. There is an application node for the RF connectors in general existing that explains a lot on the geometry of the tracks and how to do all that, how to optimize that. But there is not one that is specified only on UMRF. But if you have a need or questions on the use of UMRF, how to do, you can also, of course, contact us and we will try to help you out, or at least to point out where to put a look at and where we can help you.
Okay. So yeah, I can also, in the meantime, share the link to our app notes on our homepage. But yeah, then let's go on with the next question. What is the status of the use of PTFE?
Yeah, that's a very nice one. I was asked also a couple of weeks ago when we did some live seminars with customer, and there has been some worries about, because there is something in discussion that probably there should be something that PTFE use in the future should be limited or forbidden regarding to ROS and REACH restrictions. So it's not decided yet. That's the point. Finally, I think it will turn out into something related, probably like the lead in the brass, which is an exception that is ongoing. I know that we are already working with what you call it, replacement materials, and trying, because this will have effect on the geometry of connector and needs to be prepared. But they are not available in a huge amount at the moment at the market, because the industry is not expecting that this change will come up that fast.
So yeah, then I would say this is already the end of our webinar. Thank you very much again for your attention, and I hope you liked our webinar. Also, many thanks again, Thomas, to you. It was a pleasure again.
Very welcome.
So I hope you will hear us at our next webinar, and I wish you a good day. So thank you and goodbye.
Bye-bye.